To follow our previous talk, we have RISC-V. So, ladies and gentlemen, please put your hands together for Arun Thomas. Thank you.
Thank you. So my name is Arun Thomas. I'm a researcher at Draper Laboratory in Cambridge, Massachusetts, and I'm also the Software Task Group Chair for the RISC-V Foundation. So my talk is titled RISC-V and Rust, Embedded Systems Done Right. Sorry, let me switch here. So just out of curiosity, how many of you have heard of RISC-V? Show of hands. Okay. We're doing our job, so it seems like we're getting the word out. How many of you have played with RISC-V hardware or in emulation? Okay, a few people. How many of you read one of the RISC-V specifications? Okay, a couple people. How many people of you have hacked on Rust for RISC-V targets? These guys. Okay, nice, very good, cool. I'm hoping to get that number up. By the end of the conference, my goal is to get all of you raising your hand during the Impl days and all that stuff, so that's why I'm here. So this conference is great, man. It's a really great community. Rust Embedded is really cool. The Oxidize organizers have done a really great job getting the word out. 100 people, it's pretty impressive. And they've done such a great job that around the corner, there's a currywurst stand that has a special Rust sausage. I don't know if you can read that in the back, but it says Rust roasting sausage for only €3. And so man, I don't know how they organized that, but it's pretty impressive. So I assume this sausage is probably made of crab or something, I don't know, but if you guys are interested, it's right around the corner, literally, Checkpoint Curry 207. Full disclosure, I get a small commission if you go there, so please consider dropping by after the conference. So yeah, great conference. Thank you all for organizing. So here's my talk overview. My goal, as I said, is to get you all hacking Rust on RISC-V. I'll start off by telling you why Rust and RISC-V. I think most of you know why Rust is interesting. I'll tell you why RISC-V is interesting. Then I'll give you kind of a whirlwind crash course on RISC-V. So I'm going to talk about the ISA, the hardware-software ecosystem. It'll move pretty quickly. It'll be kind of high level. If you want to actually do development, you'll probably have to do some more digging. But I'll point you to other resources you can look at to kind of learn more about RISC-V. And then finally, I'll give you sort of a Rust RISC-V quick start. There's been a lot of work on the RISC-V or Rust ecosystem. There's actually a template that you can use to do sort of quick start hacking on a RISC-V on Rust for RISC-V. So it's the ecosystem's come a long way. I mean, the earlier talk showed how much improvement there's been in the Rust embedded space, and the RISC-V has also come a long way in the last couple months, largely due to LVM support and lots of work people have been doing on the RISC-V backend. So with that, let's get started. So why Rust and RISC-V? So many of you are embedded software developers or systems programmers, and one thing you know is that embedded software is hard. Why is it hard? One, it often requires deep knowledge of software and hardware, and it often requires developing or debugging hardware. So one of my first jobs out of school was writing firmware for a device, and a lot of the devices tended to have, I spent a lot of weekends basically debugging hardware bugs. And so this is kind of common with embedded systems. You're looking at the hardware, you're looking at the software, and it's sort of inherently complex, and often you're dealing with buggy and sometimes under-documented hardware, so that makes it challenging. Embedded software is often safety critical and security critical. There's serious consequences if software is buggy. You can look at the Boeing 737 MAX, for instance, as an example of serious consequences. Actually, I was supposed to fly on a 737 MAX on the way out here. I'm glad they swapped the plane out and grounded them.
It's something for the defense of Boeing. It's not the software that was causing the problem. It's the software that's going to solve the problem.
That is true. Yeah, I hope so. We'll see. And embedded software is typically written in C or C++, mostly for performance and also for because you need fine-grained control over low-level hardware resources. You're doing bit twiddling and that kind of thing. So the problem with this is that C and C++ are not memory safe. They have undefined behavior. They're really not a great language for developing security-critical systems, but people found ways around this. You have new development methodologies. You have formal verification tools. You have basically sort of papered around the flaws of C using tools and methodologies. To talk about systems programming generally, and embedded systems programming is part of systems programming. This is a quote from James Mickens. He's a professor at Harvard. He's written a few articles for Usenix login. And so I really like this quote. I like this article in general. It's called The Night Watch, and he sort of likens systems programmers, the Night Watch from Game of Thrones, which is, timely because Game of Thrones is back in the air. And so he says, a systems programmer has seen the terrors of the world and understood the intrinsic horror of existence. And so I've been a systems programmer for most of my life, and I think it's true, man. You see some really gnarly stuff. And like a lot of it's just sort of intrinsic to systems programming. It's hard. You're working on low-level stuff. There's concurrency. There's all this crazy stuff that happens. You don't have really good debugging tools. You have to get in there and try to understand what's going on. Hardware's not documented. So yeah, it's hard. So some of the horror is sort of intrinsic to system software, but some of it is just due to the sharp edges of C. It's not a great tool. I mean, it was invented almost 50 years ago, and we're still using it. And don't get me wrong, I actually like C. I think it's a cool language, but it's maybe not the best language for, writing safety-critical and security-critical systems. So now with Rust, there's a better way. So this is a quote from Robert O'Callaghan. I think he works at Mozilla. So the quote says, "This is one note in a Rust theme. Systems programmers can have nice things." It's kind of nice to have like cargo and Rust and have a language that doesn't let you shoot yourself in the foot. So Rust has sort of opened up this new way of developing systems that makes it easier to develop secure and reliable systems. So I think Rust is, the ecosystem's coming together. It's a new language, but I think going forward, it's definitely the right way to build systems. So Rust is a powerful type system. We heard about this in the earlier talks. You have memory safety without garbage collection. You have thread safety. These are all built in the system. The compiler makes sure you don't shoot yourself in the foot, which is pretty useful. It has performance on par with C and C++. There's this idea of zero-cost abstractions. They've really done a good job of optimizing and making the language productive. There's an excellent package manager. Cargo is awesome. There's like so much stuff in there, and it makes it really easy to get up and going. And a great community. I really like the way that Rust has sort of developed this RFC process. It's very collaborative. There's a lot of discussion, and it moves very quickly. It's pretty impressive. And also, it's generally a fun and productive development environment. I think Rust is a really cool language. So that's the case for Rust. I think you all were kind of bought in. So, and I'll tell you about RISC-V and why RISC-V is interesting. So RISC-V is an open instruction set standard. So it's a specification for basically the hardware-software interface. It's a design for extension and customization. So implementations, so it's a standard. So it means it's an open standard. But you can have open source implementations of RISC-V or commercial implementations. It's up to you. The nice thing about RISC-V is there's no need to consult a legal team to use or modify RISC-V. You can't say this with some of the other ISAs that are out there. And I think this is one of the main advantages of RISC-V is the openness and sort of the kind of like power that you get as a developer. And because of this sort of like openness, you've started to see sort of a burgeoning open source hardware ecosystem. So there are a bunch of open source RISC-V SoCs and accelerators to choose from, many that will fit whatever need you have, and you can always start your own. And the nice thing about having this open hardware ecosystem, and you have languages like Rust and open source software, by combining open source software and hardware, it creates new opportunities for doing hardware software co-design. And I think this is particularly useful and embedded, where you have tight constraints on power, reliability, worst case execution time, things like that. You can basically start playing with that boundary a little bit more and sort of research and sort of explore new opportunities for co-design and meeting these constraints. And then finally, the research community is largely adopted RISC-V. I mean, RISC-V comes from the research community, but they're doing a lot of really interesting stuff that will, because RISC-V is an open standard, it's more likely that it'll transition into commercial projects. So a couple interesting things are formal verification of the full ISA and implementations. That's pretty cool. There's a number of novel security mechanisms that are out there as well. So I feel like RISC-V is sort of opening up the innovation ecosystem, sort of tightening up the cycle between getting research ideas out into industry and back. So RISC-V has a modest goal. Its goal is to become the industry standard ISA for all computing devices. And so they're looking at the low end, so microcontrollers, all the way up to higher end supercomputers. And it's really popular now for accelerators. So you're starting to see a lot of these like machine learning, deep learning kinds of things using RISC-V. People are using it for blockchain because, blockchain's out there and people are into that. And it's designed for a number of use cases. Research was its original use case. So you see a lot of, basically the academic community is using RISC-V for their research. It's used for education. People teach classes using RISC-V. I actually, back in the day, designed an instruction set that a couple hundred undergraduates had to implement. It was not a particularly good ISA, and I feel sorry for those students, but if RISC-V existed then, I would have used it. It's a much cleaner ISA. And then you're also starting to see it being used for commercial use, and I'll talk more about that. There's a lot of companies that are starting to adopt RISC-V and start pushing products out there. So the RISC-V Foundation is actually, it's grown a lot in the last few years. It has over 200 member companies. Western Digital has stated that they're switching all future cores to RISC-V. Apparently they ship 1 billion cores a year in various disk devices and storage devices and things like that. So all of those are going to be RISC-V. NVIDIA GPUs will have embedded RISC-V microcontrollers starting with their next generation. And there's a number of other companies that have announcements that haven't quite made it out there yet, but there's a lot of interest. And so I think Rust and RISC-V are both interesting, and they're more interesting together. So I really believe that Rust and RISC-V provide a good foundation for building secure, reliable embedded systems. So Rust is very safe, like the safety and productivity of Rust combined with the openness, simplicity, and flexibility of RISC-V provide a really good foundation for building these sorts of systems. And they both happen to be fun to hack on, so that's sort of a side benefit. So now that's kind of like why I think Rust and RISC-V are interesting. I'll give you kind of a quick overview of what RISC-V is. So you can blame these guys for RISC-V. RISC-V comes from Berkeley, so there's Krista Stanovich, David Patterson, Andrew Waterman, and Yun-Sup Lee. Dave Patterson, you might know from, he's written a bunch of pretty serious or pretty well-read computer architecture books. And he also won the Turing Award for his earlier work on RISC architectures, reduced instruction set computers. So he's kind of a big deal. He also set the deadlifting record in California at 60-some. So the dude's a beast. You don't want to mess with him in a lot of senses. So the origins of RISC-V, so Krista and all, the Berkeley group began searching for a common research ISA. They taped out a bunch of different chips, MIPS, all kinds of stuff. And so they were starting this new lab. They're like, okay, we should look at an ISA and we could for our new chips. And so they looked at x86 and ARM. And some of the issues were the ISAs were too complex and the IP issues made it difficult to do that. So they embarked on a 3-month project to develop their own clean slate ISA in the summer of 2010. It was supposed to be just an internal thing. And it turns out lots of people were rolling their own ISAs. And so they put up they put up the ISA it was being used in one of their classes. And people started asking them questions and finding bugs in the ISA. And they're like, oh, wait a minute. It turns out people actually want this. So they started to, okay, maybe we should actually release it out into the world. And so 4 years later, the 3-month project turned into a much larger project. And so they released the frozen user specification in May 2014. And then the RISC-V Foundation was formed in August 2015 to kind of take this beyond Berkeley. So the RISC-V ISA, the reason why it's called RISC-V, the V is actually the Roman numeral 5. It's the 5th RISC ISA from Berkeley, so they've done a lot of these different architectures over the years, and so that's why it's called RISC-V. The idea of the ISA is it's a modular ISA, so you have a simple base instruction set and you layer instructions on top of that. So they're 32-bit, 64-bit, and 128-bit ISAs, because why not? It turns out it sounds a little crazy to have a 128-bit ISA, but it turns out some of the data center people wanted it, so they designed it in. So the base ISA is pretty small. It's less than 500 instructions, and you have this idea of this base instruction set that you can layer standard and non-standard extensions. So you can sort of customize the ISA for your needs. So as I mentioned, there's the 32-bit, 64-bit, and 120-bit integer ISA. That's the base instruction set. There's a number of standard extensions that most cores will implement, especially higher-end cores. For an embedded use case, you might not implement any of these. So there's multiply, atomic memory operations, single precision floating point, double precision floating point, and all these instructions together are called the G instruction set. That's sort of the general purpose ISA. That's what you use if you're booting up Linux. You might not implement all of these if you're doing embedded. So you won't be able to read this in the back, but I just want to show that you can fit the RISC-V ISA on a single sheet of paper, front and back. And so it's pretty nice. It's a little bit shorter than some of the other ISAs that are out there. So it's got standard stuff, load stores, branches, that kind of thing. And so there are 32 general purpose registers, X0 through X31. You'll probably notice that a lot of this looks like it has a lot of similarities to MIPS and ARM v8, and it's because they have a similar lineage. ARM v8, I believe, was designed by one of the MIPS designers, and RISC-V also is descended from the RISC lineage, so MIPS and Spark and that kind of thing. So they all have like similar kind of lineage. So by convention, there's a X0 is a 0 register. So if you read from it, it always has a 0. This turns out to be fairly useful for RISC ISAs. X1 by convention is the return address register. X2 by convention is the stack pointer register, and X8 is the frame pointer. And we also have a program counter because all CPUs need a program counter. Quickly to show you some of the an example of what the assembly looks like. This is a program that just adds 1 and 2. So there's a load immediate instruction that loads 1 into X1, load immediate X2 loads 2 into X2, and then you've got an instruction here that adds X1 and X2 and puts the result in X3. So it's what you expect. So it looks a lot like other RISC instructions sets. You have memory operations. Since it's a RISC instruction set, you can't do memory-to-memory operations. If you want to operate on memory operations, you have to load it or you have to store it, that kind of thing. So here, what you see is you're loading the value pointed to by X1 into X0, and this is the store instruction, stores the value in X0 to the memory value pointed to by X1. So this looks pretty standard. And then you have your standard control flow, branches, and jumps. So if you've used a RISC ISA, it'll look pretty familiar to you. RISC-V has 3 privilege levels. Level 0 is user mode. That's where your applications will run. Level 1 is supervisor mode. That's where your Unix class operating systems run, like Linux and BSD, SCL4, that kind of thing. Level 2 is reserved. Previously, RISC-V had this idea of, there was some talk, well, I guess there was an initial specification where level 2 was used for a hypervisor. The designers talked more to the KVM developers, and the KVM developers told them that wasn't a good idea, so they changed the specification. So level 3 is machine mode. This is the lowest level. It's the most privileged mode. This is where your firmware runs. And this is the only required level. So a lot of embedded systems just run machine mode. RISC-V virtual memory. RISC-V, if you have if you want to support Linux, you're going to have virtual memory. So it uses standard page-based schemes that support the supervisor mode. It has up to 4 levels of page tables, and there's a hardware-managed TLB. So the MMU will do the page table walk and a TLB miss. This is different from MIPS, but similar to ARM and x86. So common VM configuration options are 32-bit virtual addressing for RV32. There's 39-bit and 48-bit virtual addressing for RV64. I didn't mention this in the slide, but if you're doing just sort of a machine mode embedded core, there's also something called PMP, physical memory protections, I think. So that's also there. It's sort of it's not paging, but it's sort of like fixed regions with permissions and things like that, which is somewhat useful. This is control and status registers, or how you sort of access like system functionality, and this is particularly useful for embedded developers. It's useful for low-level programming. So different registers for kernel and firmware. So particularly the status register is very useful, and this is used to configure things like various system properties, the memory management unit, interrupts, that kind of thing. So that was kind of a quick tour. There's much more detail in the RISC-V specifications. So the user level ISA version 2.2 was ratified. The privileged ISA, the voting period's open. I expect that to be ratified in the next month or so. And if you actually are interested in contributing to the spec, you can clone the spec on GitHub and put a pull request. So that's actually kind of cool. The process is open like that. If you're interested in learning more about RISC-V, there's also a few books. There's the kind of venerable computer organization and design, computer architecture books from Hennessy and Patterson. They're now RISC-V editions of these books, which is great. It was kind of cool, actually. So I remember the very first RISC-V workshop, I got to sit at a table with Dave Patterson, and it was kind of cool being at the same table with him because he's kind of an idol of mine. And I was asking him, oh yeah, do you think at some point you'll have like a RISC-V version of the books? And he was like, yeah, I don't know, maybe if this RISC-V thing works out, it could happen. And yeah, you can actually buy the books now, which is pretty cool. And then the RISC-V reader is also good if you want a quick kind of introduction to what RISC-V is. It's kind of great that these books are out there. I used to tell people to look at some MIPS books, basically, and it would kind of get you the flavor of RISC-V, but it's much better to have actual RISC-V resources that you can grab. So there's a lot of RISC-V hardware out there for different use cases, education, research, commercial. You've got small, low-cost microcontrollers to high-performance multi-core chips, and they're written in a variety of HDLs. If you're a hardware designer, you might have an HDL that you're more comfortable with or more interested in. So they're written in VHDL, Verilog, Chisel, BlueSpec, System Verilog. They're Python-derived HDLs as well. There's it's kind of a renaissance in hardware description languages nowadays. So the original RISC-V SoCs are straight out of Berkeley. Apologies to NWA. The rocket chip is sort of the original RISC-V core. This is kind of what everyone used originally. And so it's a parameterized RISC-V SoC generator, so you can actually tweak the cache sizes and sort of like the way the cores sort of configured for various things, which is pretty nice. And this is sort of a standard 5-stage pipeline. Later, Berkeley created the Boom out-of-order core, which stands, I think, for the Berkeley out-of-order machine. And Boom is kind of cool. There weren't a lot of open source out-of-order cores, so a lot of people are able to do new research because this out-of-order core exists. Berkeley also has a number of educational cores. SODER is it's a bunch of cores from 1-stage to 5-stage pipeline. So it's really simple, a bunch of really simple cores. So if you want to kind of get up to speed with like architecture in general or in implementations, this is a good place to look. And the GitHub links are here. So SyFive is this company that the RISC-V creators formed, and the idea is they wanted to take a bunch of the Berkeley cores and sort of build custom RISC-V silicon out of them and continue developing them. And so they're building on Rocket Core and Rocket Chip SoC, and they're creating some new stuff as well. They have a couple different lines. There's the Freedom Everywhere. I actually think their naming scheme isn't particularly useful, but they've got the Freedom Everywhere and the Freedom Unleashed. I don't know. It's a little bit confusing, but I don't know. So the Freedom Everywhere is the 32-bit microcontrollers, because I guess microcontrollers should be everywhere. And the Freedom Unleashed is 64-bit multi-core SoCs. These are things that run Linux because I guess Unix has to be unleashed. I don't know. But yeah, so that's, you can grab their stuff from GitHub, and you can also buy their hardware. I'll talk more about that. But they're kind of one of the main companies that are producing RISC-V hardware. So this is a popular RISC-V embedded board from SyFive, the HighFive 1. It's the first kind of generally available open source RISC-V silicon. There are a bunch of people building test chips, but this is the first one where you can actually go on crowd supply and buy it. It's Arduino compatible, and a new revision was released this month. I ordered mine, but it didn't come in time, so no demo, sorry. And it's supported by Zephyr and FreeRTOS. The SyFive HighFive Unleashed is the kind of Unix class board. It can run Linux and BSD. And it features 4 64-bit U54 general purpose cores and an E51 embedded minion core. And these cores support the RV64GC instruction set with virtual memory and user supervisor machine mode. So it basically has all the hardware you need to run Linux. There's also a bunch of FPGA dev kits that you can use. This is the RD board, and I think on the right is the VC707 that the SyFive guys showed running Doom. So a lot of the hardware development people tend to do FPGA development. So most of my RISC-V work is on both in simulation and on FPGA. Another cool project is called FireSim from Berkeley. It's a cycle-accurate RISC-V FPGA emulation infrastructure that runs on AWS EC2 F1 instances. So these are Xilinx FPGAs that run in the cloud. And they've used it to simulate a 1,000-node data center. And this is actually pretty hard to do without this kind of infrastructure. So it's pretty cool. You can find more information. There's a blog post on AWS, and then there's a bunch of videos on the FireSim website. But this is really cool stuff. Many of you may have heard of LowRisk. It's founded by the Cambridge Raspberry Pi folks, which I'm sure you all know. And their goal is to build a completely open source SoC. Alex Bradbury gave a talk at FOSDEM in 2015 about this, and I think it's a really cool project. And by the way, they're hiring, so if you live in Cambridge or want to move to Cambridge, they're looking for people. And if you're a talented person who's interested in RISC-V, you should definitely reach out to them, because they do really cool stuff, and they're all good people. And you can find their stuff on GitHub. So Shakti is an interesting project. So RISC-V apparently is a standard ISA for India. So India is really like investing in RISC-V. So IIT Madras received $90 million in funding to build 6 open source cores. And they're building actually microcontrollers to supercomputers. And they're using an HDL called BlueSpec System Verilog. And you can find their stuff on Bitbucket. There's also a bunch of other RISC-V SoC cores. So as I mentioned, Western Digital is like transitioning all their stuff to RISC-V. So they recently released this Swerve core. Interesting name, but yeah, so that's out there. ETH Zurich has a number of interesting cores that are out there. They're also hosting the next RISC-V workshop. So there's a RISC-V workshop in June. So if you don't mind going to Zurich in June, you should check it out. Cliff Wolf has a Pico RV32 implementation. It's sort of a low-end core. It's probably interesting for some of the use cases that you might have for embedded. And I mentioned earlier, NVIDIA GPUs are going to use this Falcon RISC-V microcontroller going forward. And there's a lot of like other open source and commercial cores. The full list can be found at the RISC-V cores list on GitHub. The number of emulators and simulators, Spike is kind of the original simulator for RISC-V. It's kind of called the golden model. If you're doing RISC-V stuff and you want to implement some, like play around with some new hardware features, it's not a bad place to start there. But probably most of you are going to use QEMU if you're using emulation because it's a full-featured emulator with lots of debugging features and kind of the standard for this sort of thing. TinyMU is actually pretty cool. It's from the original developer of QEMU, Fabrice Villard. You're able to boot a full RISC-V based OS in your browser, so you can actually go to his website, you can boot a Fedora and build root images. It's pretty sweet. Fabrice Villard is like kind of a wizard. It's pretty impressive technology. And then finally, there's Gem5, which is used by computer architects and researchers, computer architecture researchers. In terms of toolchains, there's been a lot of progress in the RISC-V ecosystem. We've gotten a lot of stuff upstream, so you can actually get, if you grab upstream bin utils, there's RISC-V support as of 2.28. GCC has upstream RISC-V support as of 7.1. Clang and LVM have upstream RISC-V support for RV32 as of 8.0. And RV64 was merged a few months ago and will be released in 9.0. And it turns out the LVM status is particularly important for Rust because Rust relies on LVM. With respect to operating systems and firmware, there's a number of firmware options: Core Boot, U-Boot, the Berkeley bootloader, OpenSBI is a new project. For operating systems, there's upstream support for Zephyr, FreeRTOS, RTEMS, SEL4, Gnode, Linux, FreeBSD, Helenos, and there's a Talk port in progress, which I'm particularly excited about. For Linux distributions, it's Fedora, Debian, OpenSUSE, Yocto, OpenEmbedded, and Alpine. There's a number of resources if you want to learn more about RISC-V. There's the Getting Started guide if you want to learn how to hack on Linux and Zephyr. There's the GitHub mailing list. There's a RISC-V workshop, proceedings, and Stack Overflow. There's a couple papers that appeared in Microprocessor Report that talk about the RISC-V ISA and the philosophy. And then there's also a paper in IEEE Micro that talks about the kind of an agile approach to building RISC-V microprocessors if you're more into hardware design. So that's it for like the RISC-V overview. Now I'll quickly go into how to start hacking Rust on RISC-V or for RISC-V targets. So Rust 32-bit support for Rust, for 32-bit support went into for RISC-V went into Rust in Rust 1.1.30. And this is the pull request. You probably can't read in the back, but it went in around August-ish. And so this was pretty cool. And then 64-bit support went in 1.34, which was released pretty recently. And I'll just show kind of some snippets from the, you probably can't see this in the back, but I'll kind of read it out. But it was kind of cool to kind of see what had to happen to get the support in. And so basically, there's a couple of targets that were added. So for 64-bit, there's RISC-V 64 IMAX, so integer, multiply, atomics, compressed, and then also RISC-V 64 GC was the other target that was added. So that's the kind of like Unix-capable core. And then there's this like target description that you won't be able to read in the back, but it kind of describes, I had to look this up because I didn't actually know what this was, but it turns out it's an LVM target description. So you tells LVM basically, this is a little Indian architecture, this is how big the integers are supposed to be. It's and various widths of different various data types and things like that. So I thought this was kind of cool to see exactly this is how you add a port. It also has optional features for different pieces of the instruction set. So I thought this was kind of cool. So if you want to dig into this more, you can just take a look at the pull request. So this was actually a lot of work to get all this stuff in. So many thanks to the Rust embedded RISC-V teams and the LVM teams for making this happen. It was a tremendous amount of work. There is actually a handy Quickstart template for bare metal Rust RISC-V development. So if you clone this from the RISC-V Rust organization, it includes several example projects, including a Hello World to UART. The first thing you want to do, step 0, of course, is to install Rust. Step 2 is to add RISC-V target support for your target, the target that you want to develop for. In this case, example is for RISC-V 32 IMAC, which is what is typically used on a lot of these RISC-V embedded developer boards. Then you probably want to install some handy binary utilities, for instance, like for bin utils and that kind of thing. Then you want to install a RISC-V GNU toolchain for GDB. SyFive has pre-built toolchains that are available because GDB occasionally is a little bit of a pain to build. And then if you're using real hardware, you want something like OpenOCD or JLink so you can actually load the program onto your board. So OpenOCD binaries are available from SyFive. Turns out I misspelled from here. All right, that's cool. And then JLink can also be downloaded from Sager for the new SyFive boards. Then if you're not actually using real hardware, you can also do development on QEMU. QEMU actually has really good upstream support for RISC-V now. Some Linux distributions have also packaged up QEMU and RISC-V. So now that you've got all the preliminaries out of the way, you can clone the RISC-V Quickstart template. Basically, all you have to do is build and load the binary. So there's a handy target. You do your standard make build and make OpenOCD and make run. We'll do that. And then if you run the upload script or upload thing in GDB, it'll upload it, and you can run it and sort of run an interactive debug session. If you want to build and run on QEMU, it requires a little bit more, some minor tweaking of the cargo config. You basically tell it what QEMU command line to run. You tell it to run no graphic, and the machine is SyFive, and you pass it the kernel option. And if you run make build and make run, you can actually run this stuff on a emulated QEMU RISC-V. So this is great for bare metal, but what about other OS targets? So currently there's only bare metal support. Linux RISC-V, Linux RV64 should start coming together. And this might be a good project for the Impl days. I think basically all of the support is there. There's some more engineering to do. So at least in terms of LVM and the rest of it, there's enough support. And there's also a talk port, which is in progress. And I'm very excited about talk. I'm really interested in hearing the talk this afternoon about talk because I think it's a really interesting platform for building embedded systems. So in summary, Rust and RISC-V are a great combination for embedded systems development. Rust makes systems programming safer and more productive. And RISC-V provides new opportunities for hardware customization. Rust support for RISC-V is coming together nicely. You should give it a try. It's actually pretty easy to get going on Rust RISC-V hacking. So yeah, takeaway, please give Rust on RISC-V a go. Thank you.
So I think we've got time for a couple of quick questions, and then we've got one more talk before we get into lunch. So I saw a hand at the back.
The question, I think apparently I misspoke. I said there were less than 500 instructions, which there is less than 500, but it's true. But the slide said less than 50, and it is actually less than 50. I'm sorry, I'm still pretty jet lagged from my flight from Boston. So there might be other inaccuracies in the talk, so I apologize for that. I need more caffeine. Yeah, that's a good question. So the question was about whether SVD was going to be standardized across the RISC-V ecosystem. I don't know that there's necessarily plans to do that, but part of it has to do with the, so the platform specification is sort of coming together, but maybe that will become part of that effort. But I don't know of any efforts to standardize on SVD across the ecosystem, but it's maybe not a bad idea. And if SyFive is leading it, it's more likely that that will happen. So there's a number of commercial cores that are out there, particularly from folks like Western Digital. There's people like BlueSpec. You can get commercial cores from SyFive. You can get either sort of IP from them, or they can tape out a chip for you. So there's a few different vendors. There's also other companies like Espressive and others who are releasing other IP and can build custom cores for you. But in terms, NXP is also another vendor that has RISC-V stuff. So there's a lot of people building commercial RISC-V cores that are out there. If you look at that RISC-V cores list, there's more details on that.
Okay, please put your hands together. Arun.